Hello. As predicted earlier, we will be continuing with the central force case, but first and foremost, we have the most useful theorem that we can speak of, which is useful in variety of physics problems, and that is the Virial theorem that I have written over there. And the Virial theorem will first deduce the theorem and then use it to discuss the property of the central force as a special case. Now, for any given system of particles having position Ri and a force that is applied to it, supposedly Fi, the Newton's second law gives us that Fi will be equal to the rate of change of momentum, which can be taken as Pi dot. Now we introduce a quantity, let that be lambda, and that will be equal to the sum of Pi with Ri. So this is the dot product of the momentum with the corresponding position. Now the total time derivative of this term lambda, now we have assumed this, so we will be using a word let. So let lambda be equal to that quantity which is the dot product of the position with the momentum. And these are all vector quantities, so dot product is quite proper. And even in this case we have the dot product. So this is Pi dot. Now if we take the time derivative of lambda, then we end up with Pi dot Ri dot, and this is the first case, while in the second one we have sum over I Pi dot with Ri. The first part of the equation, that is Pi Ri dot, that can be further written as Pi dot Ri dot, take the vector form first, and the sum of that would give us, now Pi as we know is simply Mi Ri dot, the momentum, that is multiplied to the velocity being Ri dot in that case, and that again dot product with Ri dot is going to give us Mi Ri dot squared, which is nothing but the velocity MIVI squared. So this is going to give me, well, had that been half MI Ri dot squared, then it would have been T, that is the kinetic energy term, but because this is not the half, the double of that, so this is 2 times of the kinetic energy. And this is the first term that we have over here. Now the second term, as for the second term, what we'll have is sum over Pi dot with Ri. Now Pi dot is the force Fi, that is from Newton's second law that we had just discussed over here. So Fi dot Ri is nothing but the energy term or the work that is done. So what we have got over here is that d lambda over dt is nothing but d over dt of for lambda we are again taking the form Pi dot Ri, and that is equal to 2t, the first term over here, this one, plus the second term being the summation of the Fi Ri, all of that over I, of course. So this is the value of d lambda over dt. Now if we take the time average, if we are to take the time average of the above equation, what we end up with is we integrate this entire thing over time, but we cannot just do that. We have to take the average over time, so we are considering a factor tau. We'll let you know what tau is, and this is integrated from 0 to tau. Tau essentially here is the time period. The time period means that for a periodic motion, the time period obviously suggests that the motion repeats itself after it has traveled through a time from 0 to tau, and that is exactly what we have represented in the equation over here. And so that will lead us to 0, of course, on the left hand side. Now as for the right hand side case, what we write it as, because we are taking the average, so we will give a barred expression to d lambda over dt, and that will give us 2t and the average of it, the time average, then followed by fi ri summed over and the time average of it as well. Now on the left hand side, as I had said, that for a periodic motion, in case of periodic motion, what we get is that the motion repeats itself after it has gone through a time from 0 to tau, which is the time period in this case, tau being the time period. So because we are taking the limits from 0 to tau, the expression that we are going to get, that is lambda of tau minus lambda of 0, that is going to end up with a 0, of course. And so we have 2t barred plus the summation over I of f of I dot ri, that is equal to 0. So what that gives us is that that results in t bar to be equal to the negative half of fi dot product with ri, and that's the case with Virial theorem. This expression that we have achieved over here is the Virial theorem, as I said, and the term on the right hand side is known as the virial of Clausius. So this is the Virial theorem, and this term over here is known as the virial of Clausius. We are more concerned with the Virial theorem on the whole form of it. Now this can also be applied for a non-periodic motion. The condition that we consider in case of non-periodic motion is that the coordinates and the velocities of all the particles remain finite. So there is an upper bound to the quantity lambda. And by taking this tau, the time factor, to be large enough, the left hand side of the equation, which is this value over here, the 1 by tau, with tau going to very large value, that reduces the left hand side of the equation to 0 itself. So that is the condition that we must consider in case of non-periodic motion. So the result is always the same, where the left hand side of the equation is going to 0 and the right hand side containing the kinetic and the potential energy terms is going to be equal to, the sum of them is going to be equal to 0, and as a result of that, what we are having is the time average of the kinetic energy is equal to negative half of the time average of the potential energy term. I've forgotten the average over here, so let me take the average, time average, that is represented by the barred notation. So FIRI dot taken sum over minus half on the left hand side of it, and it is completely set under the bar, which represents the average or the time average over the entire time period. Now Fi, as we know, is a conservative force in case of the central force cases. So Fi is equal to the negative of del V over del R. That is the partial derivative with respect to the potential. And as a result of that, if we apply this to this case over here, So what we are going to end up with is T bar will be equal to the negative half, which is always there, and in this case for F we are taking, that is for the conservative force, we are taking del U, the potential energy, del U over del R. It's not V, we are taking it as U. So del U over del R, and that's for the conservative force, and R capped give the unit vector in that direction, that when dot product with the R vector is going to give us the same thing. So this is a vector form, and vector form over here is need not be given because we have R cap to represent the vector and the whole average of it. So we have T bar to be equal to half of the del V over del U, not del V, del U over del R times of R vector, because R cap with dot product with R is going to be R itself. And so we have this to be the energy term, and we need not give the vector notation any further. So this is another form of the Virial theorem which associates the potential energy with the kinetic energy term. Now from this we can apply it to the various forms of the forces as well as the energy terms, and we can establish a relation between them. As you will be noticing, we'll be taking the popular expression of the inverse square law for the force, and we'll be obtaining the relation which will be quite familiar if you would observe it closely. Now here's a vacant space there at the top right corner, so I'll be using that to discuss this small part that is left for this theorem. So if you remember what we had considered, the case of potential energy, we had taken it to be equal to a form where we had a r to the power n plus 1, and this was while discussing the closure relation. The video that the video before this video, that is the third installment or probably the second one, where we had discussed the closure relation. Then we followed it up with the artificial satellites, and then this theorem that we are discussing in this video. So 2 videos back I discussed the effective potential energy, and the exact potential, actual potential energy was taken in this form. And from that, if we apply it to this theorem where we have T bar to be equal to half times of that thing, that is del U over del R. Now del U over del R is going to give us the derivative of this U. So we have the derivative of U with respect to R as n plus 1 times of the constant term remains as such, and then further we have left R to the power n, and another R which was there in this case over here, and the average of that. So that gives us n plus 1 over 2, and the rest of the term, that is a r to the power n plus 1 taken average, that again gives back the potential energy term. So what we obtain here is T bar to be equal to n plus 1 divided by 2 times of the average of the potential energy. Now this expression, if we apply it to the case of the inverse square law of the force, where for the inverse square law we have the expression for the force where we have n to be equal to minus 2, because it is inverse of the square, so n will be minus 2 in that case. And applying that, what we get is the average kinetic energy is going to be minus 2 plus 1 divided by 2, the average of the potential, which gives us T bar to be equal to the negative half times the potential energy. And this is exactly what we have obtained in case of if you have derived the energy for for the even for the gravitational forces, or in case of electrons moving around the nucleus in atomic physics, the conditions are uh, quite remarkably exact. And that is what the virial theorem is all about. It's very, very essential and effective in case you have some doubts regarding the formation of the or the expressions in the energy. Then this may come to a great help for you. And the equation that will help us is the one that I have ticked just now, the right hand side top corner, the boxed term, where we have T bar to be equal to n plus 1 divided by 2 u bar, and n here uh, being the power term of the radial component or the position vector in case of the forces that are involved. And these are obviously the cases to be considered for the conservative force, else we won't have the derivative of the potential energy to be equal to the force. So overall, this theorem is very important to us in terms of understanding the concept behind the relation between the kinetic and potential energy terms. Now, dealing with central forces, we may also consider the scattering in a central force field. Now, the problem of scattering of particles at atomic scale in a central force field is extremely important in modern physics. The scattering of the beam of protons or alpha particles by the atomic nuclei of a target is an interesting problem that is dealt in nuclear physics. The problem is obviously quantum mechanical, but it can be dealt classically because the procedures for dealing the scattering problem in classical as well as quantum mechanics are quite similar. Now, the classical study of the scattering problem gives a chance for the beginner to learn the language of the problem. So let us consider a uniform beam of particles as we have shown in the figure on the left hand side. They are moving along the x-axis in a central force. All the particles of the beam have same mass and energy, represented by those parallel lines, arrow indicating the direction of motion. Now, the intensity of the beam is I naught, supposedly. We will be writing that down later. And it is the number of particles that is crossing per unit area, per unit time, normal to the direction of the beam. And it is known as flux density. And we assume that the force between an incident particle and the particle at the center of force falls off to zero at large distances. So it is mostly the form of inverse square. Now, when a particle approaches the center of force, it will interact, like in the case of the alpha particles that experience the repulsive force. And this is exactly the diagram that we consider in case of the alpha particles supposedly reacting to the repulsive force and thereby getting deviated from their path. And the deviations have been given and the angles concerned have been mentioned. So we move over to the explanation of the diagram that is at hand. So the alpha particles, while approaching, represented by those arrows, we consider two such beams. And the closer the alpha particle, that is the beam down below this one, that is, it will be deviated through a greater magnitude than the beam that is, or the alpha particle that is coming above it. So this one gets deviated as it approaches this cross section, which is the central force cross section, which is about to repel it. So this gets deviated along a certain path like this, while the other one that is a bit above and a bit away from the central force, and as a result of that will get deviated, that will definitely get deviated, but it will get deviated through a lesser angle of deviation. just like that. And as a result of those deviations, what we observe is that the line from which they have been deviated, supposedly this line from which this first lower below has been deviated, and we are taking that point exactly at the scattering center, which is represented or marked below, and the angles thus involved will be the same. So this complete angle that is considered for this deviation from its original path is phi, while the angle that is between those two alpha particles, one and above this angle, so this angle that we have over there, that is going to be d phi, the smaller angle. The similar case has been taken from the scattering point over here, scattering center, and from that, if we extend the cross-sectional area, which is the scattering center, if taken as the origin, we have the cross section of scattering to be having a position r with respect to the scattering center, as can be seen from that red mark r, that being the position of the scattering cross section at that point. We have the angle that is subtended for the whole deviation to be phi, while the angle subtended by this cross section of scattering to be equal to d phi. So that is the scattering cross section, and the thickness of the scattering cross section, as it can be seen, will be equal to the radial distance multiplied to the angle subtended, which is equal to r d phi, as written in those curly braces, closing curly braces, r d phi on the right hand side. And thus the radius of the scattering cross section will be the strip of the scattering cross section that we have. The radius will be r sine phi, that is the vertical component of the r, or the position vector, that is for the scattering cross section with respect to the point of scattering, or the scattering center. Now, as we can see that we have a certain scattering angle over here, that is phi. Phi here is the scattering angle, that is the angle through which the approaching positive charge is scattered by the target atom. So this area of cross section, or this scattering cross section that we see over here, the strip, the circular strip, that is for a target atom which presents its nucleus to the approaching alpha particle, approaching in those parallel lines that we see. The nucleus of the target atom being positive, it repels the approaching alpha particles, and the scattering angle at a certain instant or under a certain condition that we are observing here is given as phi. Now, it's not the case that we observe this in 2 dimension. Obviously, we are observing this in 3-dimensional space. So the angle that, or the angle subtended by the scattering cross section over there, won't be the small angle d phi, that is differential of the scattering angle. It will be something in 3-dimensional, because phi here is the 2-dimensional angle. The 3-dimensional angle is in the form of a solid angle. So we have d omega, omega being the solid angle involved. We have d omega to be associated with d phi in the form 2 pi sine phi d phi. Well, where do we get this from? Well, this is obtained from the relation. I'm showing it over here. So if we know that d omega being the solid angle is equal to the area subtended by a given area subtended in a given space over r squared, the r being the radial distance in that case. And this ds is equal to r sine phi, as the radius that we see over here, multiplied to d phi, that is the thickness of that area of cross section that we have given in that case, not only d phi, it is actually r d phi. So I write down an r d phi over there. Correction. Now, this constitutes the radial thickness, and the circumference, when considered, is over the entire strip, that is 2 pi of times of this radius. So this is 2 pi times of all of that divided by r squared at the denominator, and what we get is the expression that we have written just below, which is 2 pi. The r terms get cancelled out, the r over here, the r over here get cancelled out with the r square in the denominator, and we have 2 pi sine phi d phi. Now that's the expression that we have written just below, which is the relation with the solid angle, or the differential of the solid angle. Now, this incoming beam that we have, as I said, we have the intensity I naught as the flux of the particles per unit area, which is taken per unit time as well, and they are towards the they approach and towards the scattering center. Now the scattering center represents an area d sigma, which is perpendicular to the path of the beam. So the scattering center supposedly presents an area d sigma perpendicular to the path of the beam, such that whatever particle hits d sigma area, that is scattered into a solid angle d omega. Scattering the particles in solid angle d omega. So that's the area that is presented by the d sigma. The scattering center presents that much of area, thereby scattering it through an angle d omega. D omega obviously cannot be represented, the conical area that the conical angle, solid angle that we have in 2 dimension, it is difficult to represent that. So we have instead represented the d omega in terms of d phi that we have shown in the figure. So what we end up with is that the 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 sigma I of omega is something we say is the intensity of the scattered particles, and it is the number of particles that is scattered in the direction omega per unit solid angle per unit time. So then the number of scattered particles in that small solid angle d omega about this solid angle omega can be given as I naught d sigma, and that will be equal to I omega times of d omega. This is the number of particles that have been scattered in that small solid angle d omega, with the incoming intensity being I naught, and a part of that, which is d sigma, the area that is presented by the scattering cross section, allows I naught times of that area to be scattered in that cross section. So what we essentially have is that d sigma by d omega is equal to I of omega, that is the intensity of the scattered beam in that region d omega, over the incoming intensity, and this is what we call as the differential scattering cross section. So this is the differential scattering cross section, which is the derivative of the scattering angle provided by the scattering area provided by the scattering center with respect to the scattering angle, solid angle d omega. And this is usually represented by the notation sigma over omega. So the total scattering cross section will be represented as only sigma, which will be an integration of sigma for the given d omega over the d omega integrated through the entire range of it, and that will be equal to d sigma over d omega times of d omega integrated. So d sigma is all that is left, and that integrated gives me the total scattering cross section in this case. Now the objective will be to consider the two-dimensional case, which is easier than considering the three-dimensional case over here, because the diagrammatic representation does not give any help with the three-dimensional approach. So what we have over there, if you mark in the given figure, we have a term which is B, and that is known as the impact parameter. Now the impact parameter tells us that it's a measurement, obviously parameter giving a measurement. And what kind of measurement is it? Well, it gives us that it is the distance from the axis, here the axis being the x-axis. So the central axis of the scattering, that is providing the force, scattering force to the incoming alpha particle, that distance corresponds to a certain angle through which the alpha particle is scattered. So it is the perpendicular distance from the axis of the central force. Now this perpendicular distance obviously will be greater for a particle which is above that. Now in this case, as we see, B is for the particle that is coming over this line, but the line above that will have a greater value of B, and the distance between them that we have considered for that small cross section that we see over there in this circle, that is dB. So the distance being dB and the radius in that case is B. So what we get is that we can obtain a relation. We have the value for the I naught d sigma, which is d sigma is the d sigma being the area that is provided by the scattering center, as we said. So I naught times of d sigma gives us the total number of particles that are approaching through that small segment, and that will be equal to I naught times of, if we consider that segment, because they have the same angular value, that is d phi. So as you can see, d phi is the angle in that case for that is existing between those two after they are being scattered, that is represented over here, and phi is the angle of deviation with respect to the scattering center that we have indicated over here. So what we get is I naught d sigma is equal to I naught times of 2 pi b dB. Why? Because 2 pi b dB is the circumference and the area that is subtended by that strip, which is going to give us a d sigma in that case. So this is the value. Now we have I naught d sigma to be equal to I omega d omega. So we get I of omega d omega to be equal to I naught two pi b dB. But as we know that I omega d omega is nothing but equal to I naught sigma omega d omega, and that is equal to the right hand side term, but we'll go to the right hand side term later. Now because we have expressed the value of d omega over here, so what we get is I naught. Now the sigma can be taken as the function of phi when omega is converted to the phi value, that is 2 pi sine phi d phi, and that is equal to this right hand side term, that is I naught 2 pi b dB. Now all of that was fine until what we get is that if we are increasing the value of this impact parameter b, the value of phi is going to decrease. Why? Because it is the value of b increasing means that we are going far from the center of the central force. So as a result of that, the value of the scattering angle is going to decrease drastically towards the end, and it is finally going to be in fact 0. So as a result of that, what we get is that relation that we have over here, that will be in the negative form. So it will be proper to introduce a negative notation to it. So that means we have the right hand side term, which is I naught times of 2 pi b dB, and that will be equal to the negative of the left hand side that we had written, that is I naught sigma of phi 2 pi sine phi d phi. And those terms, the 2 pi terms cancelling, the I naught terms cancelling, what we end up with is that sigma of phi, that is the scattering cross section over that strip that we have represented in the diagram. We have eliminated the d omega, that is the solid angle term, and we have reduced it to the plane angle phi. So it is over phi in the range from phi to phi plus d phi now, and so this is the cross section, which is equal to the negative of, what we are left with is b divided by sine phi, and in the bracket we have the differential of the impact parameter with respect to the scattering angle that is considered over here. So this is the important relation in terms of the plane angle, that the two-dimensional angle that we have in the given figure. We have the expression in terms of the solid angle as well, which is given over here, and also the expression for solid angle, which gives the differential form of the scattering cross section over here. So all of these cases that we have considered over here are going to help us to when we study the case of Rutherford scattering cross section, but that is to be considered, or that is to be dealt in the next video in the series. Till then, thank you for watching.